Imagine you have the most powerful microscope ever built. Not just any microscope, but one that can zoom in forever. You start by looking at your hand. You see the skin, the tiny ridges, the pores. You zoom in further. Now you see cells, thousands of them packed together like bricks in a wall. You keep going. Now you see molecules, the chains of atoms that build every living thing. Deeper still. Now you see individual atoms, those tiny spheres that make up everything you have ever touched, tasted, or breathed. But you do not stop. You push further into the atom itself. You see the nucleus, impossibly small compared to the electron cloud surrounding it. You zoom into the nucleus and find protons and neutrons. Deeper still, you find quarks, the fundamental particles that build protons and neutrons. But here is where things get strange. You want to keep going. You want to zoom in further. You want to see what space itself looks like at the very deepest level. And then suddenly, your microscope breaks. Not because of any technical failure. It breaks because the universe itself will not let you see any further. There is a wall. A fundamental limit. A point beyond which the very concept of distance stops making sense. That point, that wall, that ultimate limit is called the Planck length. It is a distance so incredibly tiny that it makes atoms look like galaxies. It is so small that if you tried to measure anything smaller, you would accidentally create a black hole. And today, we are going to take the deepest journey possible into the fabric of reality itself to understand what this mysterious length really means, why it exists, and what it tells us about the true nature of the universe. Before we dive in, let me give you a sense of just how small we are talking about. The Planck length is approximately 1.6 times 10 to the power of negative 35 meters. That number means nothing by itself, so let me put it in perspective for you. Take an atom. A single hydrogen atom. It is already unimaginably small. You cannot see it with any optical microscope. It is about 1/10 billionth of a meter across. Now imagine you could blow up that atom to the size of the entire observable universe. The observable universe is about 93 billion light-years across. If a single atom were expanded to that enormous size, the Planck length would be roughly the size of a medium tree in a forest. That is how small the Planck length is compared to an atom. We are talking about a level of smallness that is almost violent in its extremity. Here is another way to think about it. There are more Planck lengths inside a single proton than there are protons across the entire observable universe. Let that sink in for a moment. The ratio of the smallest meaningful distance to a proton is larger than the ratio of a proton to the entire cosmos. The Planck length is not just small. It is a different category of small. It is where the word small itself loses meaning. Now I want you to think about something else. What if this length is not just a measurement? What if it is the actual pixel size of reality? What if the universe, at its most fundamental level, is not smooth and continuous, but instead is made of tiny discrete chunks? What if space itself has a resolution limit, just like your computer screen has pixels? This is one of the most profound questions in all of physics, and it remains unanswered. But the Planck length sits right at the heart of this mystery, and by the end of our journey today, you will understand exactly why. We are going to explore everything. We will start with the story of how this length was discovered. We will meet the brilliant physicist who first calculated it over 100 years ago. We will understand the mathematics behind it in a way that actually makes sense. We will explore why you cannot measure anything smaller. We will dive into the quantum foam that might exist at this scale. We will discuss whether space is truly pixelated or smooth. We will look at what the Planck length means for black holes, for the Big Bang, for the holographic principle, and for the future of physics. And we will confront some of the deepest philosophical questions that arise when you realize the universe might have a resolution limit. If you find this kind of deep exploration fascinating, if you love going beyond surface-level explanations into the real heart of physics, then make sure you are subscribed to this channel. Hit that like button, because it tells the algorithm that people want this kind of deep scientific content. And leave a comment telling me what you think the smallest possible thing in the universe might be. I read every single comment, and they genuinely shape what topics we explore next. Now let us begin our descent into the deepest layer of reality. To understand the Planck length, we need to start with a story. And this story begins not with the Planck length itself, but with a crisis. In the year 1899, the world of physics was in turmoil. On the surface, everything seemed fine. Classical physics, built on the foundations of Newton and Maxwell, appeared to explain almost everything. The motion of planets, the behaviour of gases, the propagation of light through electromagnetic waves. Physicists at the time famously believed they were almost done, that all the major discoveries had been made, and only a few minor details remained to be cleaned up. But those minor details turned out to be cracks in the foundation of reality itself, and one of those cracks was called the black body radiation problem. Here is what the problem was. Every object that has a temperature emits radiation. You emit infrared radiation right now because your body is warm. A piece of iron, when heated, starts glowing red, then orange, then white as its temperature increases. Physicists wanted to calculate exactly how much radiation an idealized object, called a black body, would emit at each wavelength for a given temperature. This should have been a straightforward calculation using the known laws of physics. But when they did the math, something catastrophic happened. The classical equations predicted that as you look at shorter and shorter wavelengths, the amount of radiation should increase without limit. This meant that any warm object should emit infinite energy in the ultraviolet range. Infinite energy. Obviously, this does not happen in reality. Your coffee cup is not blasting you with infinite ultraviolet radiation right now. This absurd prediction was called the ultraviolet catastrophe, and it was a sign that something was deeply wrong with the foundations of physics. Enter Max Planck. Max Carl Ernst Ludwig Planck was born on April 23, 1858, in Kiel, Germany. He was a man of extraordinary discipline and conservatism. He was not a revolutionary by nature. He believed deeply in the established order of classical physics and had no desire to overthrow it. His PhD advisor actually told him not to go into theoretical physics because everything important had already been discovered. But Planck was drawn to thermodynamics, the physics of heat and energy, and he could not leave the black body problem alone. It nagged at him. The equations did not work, and Planck was the kind of person who needed equations to work. For years he struggled with this problem. He tried every classical approach he could think of. Nothing worked. The ultraviolet catastrophe persisted. Then, on October 19, 1900, Planck presented a solution to the German Physical Society in Berlin. His solution was mathematically elegant but physically bizarre. He proposed that energy is not emitted continuously, as everyone had always assumed, but in tiny discrete packets. He called these packets quanta. Each quantum of energy was equal to the frequency of the radiation multiplied by a tiny constant, a number he introduced into physics for the first time. That constant is now called Planck's constant, symbolized by the letter H, and its value is approximately 6.626 times 10 to the power of negative 34 joule-seconds. This was a desperate move. Planck himself called it an act of desperation. He did not believe that energy was truly quantized. He thought it was a mathematical trick, a temporary fix until someone found the real solution. But the math worked perfectly. His formula matched the experimental data with stunning precision, and that constant, that tiny number he introduced as a mathematical device, turned out to be one of the most fundamental numbers in all of nature. It would later become one of the 3 ingredients in the recipe for the Planck length, But here is what most people do not know. In that very same year, 1900, Planck did something else remarkable. Having introduced his constant, he realized that he now had three fundamental constants of nature at his disposal. The speed of light, c, which comes from Maxwell's electromagnetism, the gravitational constant, g, which comes from Newton's gravity. And his new constant, Planck realized that by combining these three constants in the right way, he could create natural units of measurement. Units that were not based on any human convention, not based on the length of a king's arm or the distance from the equator to the pole, but based purely on the fundamental structure of the universe itself. He wrote about this in a paper, noting that these units would have meaning for all times and all civilizations, including extraterrestrial and non-human ones. The natural unit of length that Planck derived from these three constants is what we now call the Planck length. The formula is beautifully simple. You take Planck's constant, divide it by 2 pi to get the reduced Planck constant. Multiply it by the gravitational constant, divide by the speed of light cubed, and then take the square root. The result is that astonishing number, 1.616 times 10 to the negative 35 meters. Planck calculated this over 120 years ago, and we still do not fully understand what it means. That is how deep this rabbit hole goes. Now I should mention that Planck was not the very first person to think about natural units. An Irish physicist named George Johnstone Stoney had proposed natural units in 1874 using the elementary charge, the gravitational constant, and the speed of light. Stoney even calculated a natural unit of length, now called the Stoney length, which is similar in magnitude to the Planck length, but uses a slightly different set of constants. However, it was Planck's formulation, using the quantum constant h, that proved to be more physically meaningful. The quantum constant turns out to be more fundamental than the elementary charge for defining the smallest scale of physics, which is why we call it the Planck length and not the Stoney length. Let me now take you on a journey through the scales of the universe so you can truly feel how far down we have to go to reach the Planck length. We will start at the human scale, about 1 meter, and zoom in by powers of 10. Ready? At 1 meter, you have a human being. The scale of everyday life. At 1/10 of a meter, 10 centimeters, you have the width of your hand. At 1/100th of a meter, 1 centimeter, you have a marble, a peanut, something you can hold between your fingers. At 1,000th of a meter, 1 millimeter, you have a grain of sand. You can barely see it, but it is still visible to the naked eye. At 100,000ths of a meter, 10 micrometers, you have a human red blood cell. You need a microscope now. At 1 millionth of a meter, 1 micrometer, you have bacteria. At 100 millionth of a meter, 10 nanometers, you have the width of a Dina double helix. We are now firmly in the nano world. At 1 billionth of a meter, 1 nanometer, you have small molecules, maybe 10 atoms across. At 1/10 billionth of a meter, 1 angstrom, you have the size of an individual atom. This is roughly where chemistry ends and physics begins. The atom was once thought to be the smallest thing. Its very name means indivisible in Greek. But of course, we went deeper. At 10 to the negative 14 meters, 100 femtometers, you have the size of an atomic nucleus. The nucleus is about 100,000 times smaller than the atom itself. All that space in an atom between the nucleus and the electrons is empty. If the atom were a football stadium, the nucleus would be a fly at the centre. At 10 to the negative 15 meters, 1 femtometer, you have the size of a proton or neutron, the individual particles that make up the nucleus. At roughly 10 to the negative 18 meters, 1 attometer, you start to probe the internal structure of protons and neutrons. This is the scale at which you find quarks, the fundamental particles that make up protons and neutrons. Quarks are point-like, meaning we have not been able to measure any size for them, even at this scale. The Large Hadron Collider at CERN probes distances down to about 10 to the negative 20 meters. And here is where things get quiet. Between 10 to the negative 20 meters and 10 to the negative 35 meters, there are 15 orders of magnitude that we know almost nothing about. We have no experiments that can probe this range. We have no direct observations. We have only theory, mathematics, and educated guesses. This is the great desert of particle physics. 15 orders of magnitude of unknown territory, and at the very end of this desert, at 10 to the negative 35 meters, sits the Planck length. The wall. The end of the road. Now let us truly understand what makes the Planck length special. It is not just that it is very small. Many things are very small. What makes the Planck length unique is that it emerges from the collision of two great theories that currently refuse to work together. Those two theories are quantum mechanics and general relativity. Quantum mechanics is the physics of the very small. It describes how atoms behave, how particles interact, how light works at the most fundamental level. It is governed by Planck's constant h. The central insight of quantum mechanics is that at small scales, nature is fuzzy, probabilistic and quantized. Particles do not have definite positions until you measure them. Energy comes in discrete chunks. There is an inherent uncertainty built into the fabric of reality at the quantum scale. General relativity is the physics of the very large and the very heavy. It describes how gravity works, how space-time bends and curves, how the universe expands. It is governed by the gravitational constant, g, and the speed of light, c. The central insight of general relativity is that space and time are not fixed backgrounds, but are dynamic, flexible, capable of curving, stretching, and warping in response to matter and energy. These two theories are the greatest achievements of 20th century physics. Quantum mechanics has been tested to extraordinary precision. General relativity has been tested to extraordinary precision. They are both spectacularly correct within their own domains, but they are fundamentally incompatible with each other. Quantum mechanics assumes that space-time is a fixed flat stage on which particles dance. General relativity says space-time is not a fixed stage, but a participant in the dance. When you try to combine these two theories, when you try to apply quantum mechanics to gravity itself, the mathematics breaks down. You get infinities. Nonsensical answers. The equations blow up, and here is the crucial point. The Planck length is exactly the scale at which this breakdown occurs. It is the scale at which the quantum fuzziness of matter becomes comparable to the gravitational warping of space-time. At the Planck length, you cannot separate gravity from quantum effects. They become equally important, and since we do not have a theory that consistently combines them, we literally cannot describe what happens at this scale. The Planck length is not just small, it is the boundary of our understanding. Let me explain this more precisely using the Heisenberg uncertainty principle, one of the pillars of quantum mechanics. The uncertainty principle says that you cannot simultaneously know both the position and momentum of a particle with perfect precision. The more precisely you try to measure position, the more uncertain the momentum becomes, and vice versa. This is not a limitation of our instruments, it is a fundamental property of nature. Now imagine you want to measure something at the scale of the Planck length. You want to look at a region of space that is only one Planck length across. To do this, you need a probe, a particle of light or some other particle with a wavelength comparable to the Planck length. The wavelength of a particle is inversely related to its energy. A shorter wavelength means higher energy, so to probe Planck scale distances, you need particles with absolutely enormous energies. When you calculate the energy needed, you get approximately 10 to the 19 billion electron volts, or about 10 to the 9 joules. This is called the Planck energy. Now here is where it gets mind-bending. 10 to the 9 joules is an enormous amount of energy concentrated in a single particle. For comparison, the Large Hadron Collider, the most powerful particle accelerator ever built, accelerates protons to energies of about 10 to the 4 billion electron volts. The Planck energy is roughly 10 to the 15 times higher than anything we can currently achieve. It is the energy equivalent of a lightning bolt or a car moving at highway speed, but concentrated into a single subatomic particle. And here is the problem. When you concentrate that much energy into a region the size of the Planck length, general relativity tells us what happens. That much energy in that smaller volume creates a gravitational field so intense that it forms a black hole. A tiny subatomic black hole, but a black hole nonetheless. The radius of this black hole turns out to be approximately 1 Planck length. So the very act of trying to look at something at the Planck scale creates a black hole that hides whatever you are trying to see. The harder you try to look, the bigger the black hole gets, and the more thoroughly it conceals the information you are seeking. This is not a matter of building better instruments. It is not an engineering challenge. It is a fundamental limit imposed by the combination of quantum mechanics and gravity. The Planck length is the scale at which looking at something destroys what you are looking at. It is the ultimate resolution limit of the universe. Think about what this means. Throughout the entire history of science, whenever we thought we had found the smallest thing, we eventually found something smaller. Atoms were not fundamental. They were made of electrons and nuclei. Nuclei were not fundamental. They were made of protons and neutrons. Protons and neutrons were not fundamental. They were made of quarks. At every stage we broke through to a deeper level. But at the Planck scale, this pattern might finally stop. Not because there is nothing smaller, but because the concept of smaller ceases to have operational meaning. You cannot define distance below the Planck length, because any attempt to do so is defeated by black hole formation. It is as if the universe is saying this far and no further. Now let us talk about what might actually exist at the Planck scale. If you could somehow peek behind the curtain, what would you see? The honest answer is that nobody knows, but physicists have some fascinating ideas, and the most famous one is called quantum foam. The concept of quantum foam was proposed by the legendary physicist John Archibald Wheeler in 1955. Wheeler realized that if you apply quantum mechanics to spacetime itself, then at very small scales, spacetime should be subject to quantum fluctuations. Just as a quantum particle does not have a definite position, quantum spacetime should not have a definite geometry. At everyday scales, these fluctuations are incomprehensibly tiny, and spacetime appears perfectly smooth. But as you zoom in toward the Planck scale, the fluctuations become more and more violent. At the Planck scale itself, spacetime should be a seething, turbulent chaos of constantly forming and dissolving microstructures. Wheeler called this quantum foam. Imagine the ocean seen from space. From high above, it looks perfectly smooth, like a flat blue surface. But as you descend, you start to see waves. Get closer and you see whitecaps and spray. Get right down to the surface and you find a violent turbulence of water molecules constantly bouncing and interacting. Wheeler suggested that spacetime is similar. From our large-scale perspective, it looks smooth and continuous. But at the Planck scale, it is a wild quantum foam of fluctuating geometries. What does this foam look like? Wheeler and others have speculated about its structure. Perhaps tiny black holes are constantly forming and evaporating. Perhaps tiny wormholes connect different points in space, flashing in and out of existence. Perhaps the topology of space itself is constantly changing, with handles and bridges appearing and disappearing in a fraction of a Planck time. The foam is not something you could ever see or photograph. It is a theoretical prediction of what should happen when quantum uncertainty acts on the geometry of space. However, I must be clear about something. Quantum foam remains a theoretical concept. We have no direct evidence for it. Some theories predict it exists, others predict it does not. For instance, loop quantum gravity, which is one of the leading approaches to quantum gravity, predicts that space-time has a discrete structure at the Planck scale, but one that is more orderly than Wheeler's chaotic foam. String theory, another leading approach, suggests that the fundamental objects at the Planck scale are one-dimensional vibrating strings rather than foamy space-time. The truth is that we simply do not know what the Planck scale looks like. It remains one of the greatest unsolved mysteries in physics. This brings us to one of the most profound questions in modern physics. Is space continuous or discrete? Is it smooth like a line, where between any 2 points you can always find another point, no matter how close they are? Or is it granular, like a fabric woven from tiny threads, where there is a minimum possible distance between any 2 points? Our everyday experience tells us space is continuous. You can move your hand smoothly through space without jumping from one point to another. Between any 2 positions, there are infinitely many intermediate positions. This is what classical physics assumes. This is what general relativity assumes. Space is a smooth, continuous manifold. But quantum mechanics has taught us repeatedly that things we thought were continuous are actually discrete. Energy comes in quanta. Angular momentum comes in discrete multiples of Planck's constant. Electric charge comes in multiples of the electron charge. Every time we thought something was continuous, quantum mechanics revealed an underlying discreteness. So is space the same? Does space come in tiny discrete chunks, with the Planck length as the minimum possible chunk size? This is where different theories of quantum gravity give different answers, and I want to walk you through the major perspectives. The first perspective comes from loop quantum gravity, or LQG. This theory was developed primarily by Abhay Ashtekar, Lee Smolin and Carlo Rovelli in the late 1980s and 90s. In loop quantum gravity, space is indeed discrete. The fundamental building blocks of space are not points, but tiny quantum loops. These loops weave together to form a structure called a spin network, which is essentially a graph where the links carry quantum numbers describing the geometry of space. The key prediction of LQG is that area and volume are quantized. There is a minimum possible area, roughly equal to the Planck length squared, and a minimum possible volume, roughly equal to the Planck length cubed. You cannot have a surface with an area smaller than 1 Planck area. You cannot have a region with a volume smaller than 1 Planck volume. Space in this theory is genuinely pixelated, though the pixels are not little cubes arranged in a grid, but rather a more complex quantum network. The second perspective comes from string theory. In string theory, the fundamental objects are not point particles but tiny one-dimensional vibrating strings. These strings have a minimum length, which is roughly the Planck length. In string theory, you cannot probe distances shorter than the string length, because the strings themselves are the most fundamental objects. There is no meaning to asking what happens at scales smaller than a string. Interestingly, string theory has a property called T-duality, which suggests that physics at distances much smaller than the string length is actually equivalent to physics at distances much larger than the string length. In a sense, below the Planck scale, you end up back at large scales again. The very small is equivalent to the very large. The third perspective comes from causal set theory, developed by Raphael Sorkin and others. In this approach, space-time is fundamentally made of discrete events, called elements, which are related to each other by causal relations. These elements are sprinkled throughout space-time at a density of approximately 1 per Planck volume. There are no intermediate points between these discrete events. Space-time is not a continuous fabric, but a set of disconnected points connected by causal relationships. The continuity of space that we experience at large scales emerges statistically from the underlying discreteness, just as the smooth flow of water emerges from the discrete motions of water molecules. The fourth perspective, which is more conservative, argues that the Planck length might not represent any physical discreteness at all. It might simply be the scale at which our current theories break down, without implying that space itself is quantized. In this view, space could still be perfectly continuous at the Planck scale, but we would need a new theory, one that goes beyond both quantum mechanics and general relativity to describe it. The Planck length would be a limit of our knowledge, not a limit of nature. Each of these perspectives has its strengths and weaknesses, and currently there is no way to experimentally distinguish between them. The Planck scale is so far beyond our experimental reach that we cannot directly test whether space is discrete or continuous. This is one of the great frustrations of modern theoretical physics. We have beautiful mathematical theories that make different predictions about the nature of space at the smallest scale, but we cannot perform the experiments that would tell us which theory is correct. However, there are some indirect approaches that physicists are exploring, and these are genuinely exciting. Let me tell you about a few of them. One approach uses observations of light from distant gamma-ray bursts. A gamma-ray burst is an incredibly violent explosion that occurs when a massive star collapses or when two neutron stars merge. These bursts produce photons with a wide range of energies, from low-energy radio waves to extremely high-energy gamma rays. All these photons are emitted at essentially the same time and travel across billions of light-years of space to reach our telescopes. Now here is the key insight. If space is discrete at the Planck scale, then this discreteness might affect how light propagates through space. Specifically, higher energy photons, which have shorter wavelengths, might interact with the granular structure of space slightly differently than lower energy photons. This could cause high energy photons to travel very slightly faster or slower than low energy photons, arriving at Earth at slightly different times despite being emitted simultaneously. The Fermi Gamma Ray Space Telescope has looked for exactly this effect. In 2009, Fermi observed a gamma-ray burst called GARB Nu 90510, which occurred about 7 billion light-years away. The telescope detected both low-energy and high-energy photons arriving within a fraction of a second of each other, despite having travelled for 7 billion years. This extraordinary measurement placed very tight constraints on any energy-dependent variation in the speed of light. The result was that any dispersion, if it exists, must occur at an energy scale at least 1.2 times higher than the Planck energy. This was a stunning result. It effectively ruled out the simplest models of space-time granularity that predicted such dispersion. However, it does not rule out all models of discrete space-time, because some models predict no dispersion at all, just a different kind of discreteness. The search continues. Another experimental approach is the holometer at Fermilab, designed by Craig Hogan. The holometer is essentially two overlapping Michelson interferometers, each about 40 meters long, designed to look for correlations in the quantum jitter of space-time. If space is quantized, if there is a minimum meaningful distance, then position should fluctuate randomly at that minimum scale. The holometer looks for correlated fluctuations between its two interferometers that would indicate genuine space-time jitter rather than ordinary noise. As of my knowledge, the holometer has not found evidence of the particular type of holographic noise it was designed to detect, but the experiment represents a pioneering attempt to search for Planck-scale physics in the laboratory. Gravitational wave detectors like LIGO, Virgo and CAGRA also have potential relevance. While these instruments were designed to detect gravitational waves from astrophysical events like merging black holes and neutron stars, they are sensitive to extraordinarily tiny changes in distance. LIGO can detect a change in the length of its 4-kilometer arms of about 1,000th the width of a proton. Future generations of gravitational wave detectors might be able to detect even tinier fluctuations that could encode information about Planck-scale physics. Let me now take us in a different direction and talk about something that connects the Planck length to one of the most mind-bending ideas in all of physics. I am talking about the holographic principle. In 1972, Jacob Bekenstein made an astonishing discovery about black holes. He showed that a black hole has entropy, a measure of how much information it contains, and that this entropy is proportional not to the volume of the black hole, but to its surface area. Specifically, the entropy of a black hole is equal to 1/4 of its surface area measured in units of Planck areas. 1 Planck area is the Planck length squared, about 2.6 times 10 to the negative 70 meters squared. This means the information content of a black hole is essentially counted by tiling its event horizon with tiny Planck-sized squares. Each Planck area on the horizon stores exactly 1 bit of information. This is extraordinary. Think about what this means. If you have a room full of stuff, books, computers, furniture, you would expect the total information content to be proportional to the volume of the room. The more volume you have, the more stuff you can fit, the more information is stored. But Bekenstein's result says that the maximum amount of information that can be stored in any region of space is proportional to the surface area of that region, not its volume. It is as if the 3-dimensional interior is an illusion, and all the real information lives on the 2-dimensional boundary. In 1993, the Dutch physicist Gerard 't Hooft took this idea further and proposed what he called the holographic principle. He suggested that the physics of any region of space can be completely described by a theory living on the boundary of that region. The 3-dimensional world we experience would then be like a holographic projection of information stored on a 2-dimensional surface. In 1995, Leonard Susskind formalized this idea and connected it to string theory. And the resolution of this hologram is the Planck length. The boundary surface is divided into Planck-sized pixels, each storing 1 bit of information. The entire 3-dimensional universe, with all its complexity, all its stars and galaxies and people and thoughts, would be encoded in binary information on a 2-dimensional surface at Planck scale resolution. This is not science fiction. This is a well-established theoretical framework in modern physics, supported by rigorous mathematical evidence, particularly from the ADS CFT correspondence discovered by Juan Maldacena in 1997. If the holographic principle is correct, then the Planck length truly is the pixel size of the universe in a very literal sense. Not pixels of space itself, but pixels of the holographic screen on which the information of our universe is encoded. Every Planck area on the cosmic boundary contains 1 bit. The total number of bits is the total area of the boundary divided by the Planck area. This gives us the total information content of the universe, which some estimates place at around 10 to the 122 bits. That is a huge number, but it is finite. The universe contains a finite amount of information, and the Planck length sets the scale of that finitude. Now let us travel back in time. Not to the history of human discovery, but to the history of the universe itself. Let us go all the way back to the very beginning. The Big Bang. And here the Planck length appears again, in what might be its most dramatic role. According to our best understanding of cosmology, the universe began approximately 13.8 billion years ago in an event we call the Big Bang. But the Big Bang was not an explosion in space. It was an explosion of space. Space itself, and time with it, came into existence in that event. Now, when we try to trace the history of the universe backwards in time, we find that the universe was hotter, denser, and smaller at earlier times. We can trace this history backward with great confidence using general relativity and our knowledge of particle physics, all the way back to a tiny fraction of a second after the Big Bang. But there is a limit to how far back we can go. That limit is the Planck time. The Planck time is the Planck length divided by the speed of light. It equals approximately 5.4 times 10 to the negative 44 seconds. This is the time it takes light to travel 1 Planck length, and it represents the earliest moment in the history of the universe that our current physics can describe. Before the Planck time, during the first 5.4 times 10 to the negative 44 seconds of existence, the universe was in what is called the Planck epoch. During the Planck epoch, the universe was incredibly hot, at or above the Planck temperature of approximately 1.4 times 10 to the 32 degrees Kelvin. At this temperature, the average energy of particles would have been at or above the Planck energy. The entire observable universe, all the matter and energy that would eventually become hundreds of billions of galaxies, was compressed into a region roughly 1 Planck length across. Under these conditions, all 4 fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, are believed to have been unified into a single force. Quantum gravitational effects would have dominated everything. Space-time itself would have been subject to violent quantum fluctuations. The concepts of space and time as we understand them may not have existed at all. We know almost nothing about the Planck epoch. It is the most mysterious moment in the history of the universe. Our theories of physics simply cannot describe what happened during that first inconceivable fraction of a second. General relativity breaks down because quantum effects are too strong. Quantum field theory breaks down because gravitational effects are too strong. To describe the Planck epoch, we would need a complete theory of quantum gravity, which we do not yet possess. What we can say is this. The Planck epoch ended when the universe was about 1 Planck time old. At that point, gravity separated from the other 3 forces and became the distinct force we know today. The universe began its expansion and cooling, and the physics became tractable. From the end of the Planck epoch onward, we can describe the evolution of the universe with increasing confidence. But those first 5.4 times 10 to the negative 44 seconds remain shrouded in mystery. This means that the very origin of the universe is a Planck-scale phenomenon. The birth of everything, of space, time, matter, energy, all the laws of physics happened at the Planck scale. Understanding the Planck length is therefore not just about understanding the smallest possible distance. It is about understanding the beginning of everything. There is another aspect of the Planck length that I find deeply fascinating, and it involves the Planck mass. Now, when you hear about Planck units, you might expect the Planck mass to be incredibly tiny, just like the Planck length and Planck time. But it is not. The Planck mass is about 2.2 times 10 to the negative 8 kilograms, which is approximately 22 micrograms. That might still sound small, but in the world of particle physics, it is absolutely enormous. A proton has a mass of about 1.7 times 10 to the negative 27 kilograms. The Planck mass is about 10 to the 19 times heavier than a proton. It is roughly the mass of a small flea, or a grain of sand, or a tiny speck of dust visible to the naked eye. Why is the Planck mass so surprisingly large? It is because of the extraordinary weakness of gravity. The Planck mass is the mass at which the quantum wavelength of a particle equals its Schwarzschild radius, the radius at which it would become a black hole. For particles much lighter than the Planck mass, quantum effects dominate over gravitational effects. For particles much heavier than the Planck mass, gravitational effects dominate over quantum effects. The Planck mass sits at the boundary between the quantum world and the gravitational world. And because gravity is so incredibly weak compared to the other forces, this boundary occurs at a relatively large mass. This is actually one of the great unsolved problems in physics, known as the hierarchy problem. Why is gravity so much weaker than the other forces? Why is the Planck mass so much larger than the masses of all known particles? The energy scale of the Standard Model, where the other 3 forces operate, is about 10 to the 2 billion electron volts, the Planck energy is about 10 to the 19 billion electron volts. That is a gap of 17 orders of magnitude. Why does this enormous gap exist? Nobody knows. Various theories have been proposed, including supersymmetry, extra dimensions and others, but none has been experimentally confirmed. Speaking of extra dimensions, let me take a brief detour into one of the most speculative but fascinating ideas related to the Planck length. Some theories, particularly versions of string theory, propose that our universe has more than the 3 dimensions of space and 1 dimension of time that we perceive. There might be additional spatial dimensions that are curled up, compactified, so small that we cannot detect them. In some versions of these theories, the extra dimensions could be curled up at the Planck scale. Each point in our 3-dimensional space would actually be a tiny Planck-sized ball with extra dimensions that we cannot access because they are too small to explore. But some theories go even further. In the late 1990s, Nima Arkani-Hamed, Sarvas Dimopoulos, and Gia Dvali proposed a model known as the AD model, in which some extra dimensions could be much larger than the Planck length, up to a millimetre in size. In their model, gravity is weak in our 3-dimensional world because it leaks into these extra dimensions, but the other forces are confined to our 3-dimensional brain, a membrane floating in a higher dimensional space. If this model is correct, then the fundamental Planck length in the full higher dimensional space would be different from the effective Planck length we calculate in our 3-dimensional world. The true quantum gravity scale might be much lower than what we naively expect, potentially accessible to future particle accelerators. However, experiments at the LHC have not found evidence for these extra dimensions, pushing the constraints on such models to increasingly tight limits. Let us now go deeper into the mathematical structure of the Planck length and understand why those 3 particular constants, c, g, and h bar, are the ones that define it. The speed of light, c, is approximately 3 times 10 to the 8 meters per second. It is the maximum speed at which information can travel through space. It is the speed of causality itself. It connects space and time in special relativity, telling us that space and time are not separate entities, but aspects of a single spacetime. When c appears in the Planck length formula, it brings the relativistic structure of spacetime into the picture. The gravitational constant, g, is approximately 6.67 times 10 to the negative 11 meters cubed per kilogram per second squared. It measures the strength of gravity. It tells us how much spacetime curves in response to a given amount of mass or energy. When g appears in the Planck length formula, it brings the curvature of spacetime, the geometrical nature of gravity, into the picture. The reduced Planck constant, h bar, is approximately 1.05 times 10 to the negative 34 joule seconds. It measures the scale at which quantum effects become important. It tells us the size of the quantum fuzziness, the fundamental uncertainty, in nature. When h bar appears in the Planck length formula, it brings the quantum nature of reality into the picture. So the Planck length is where all 3 of these fundamental aspects of reality meet. It is where the speed of light, the curvature of gravity, and the fuzziness of quantum mechanics all become equally important. It is the unique scale at which relativity, gravity, and quantum mechanics all matter simultaneously. That is what makes it so special and so mysterious. It is the meeting point of our 3 deepest theories of nature, and it is the place where those theories refuse to cooperate. Let me give you another way to think about why the Planck length represents a fundamental limit. Consider the concept of a Compton wavelength. Every particle with mass has a Compton wavelength, which is inversely proportional to its mass. The Compton wavelength tells you the scale below which quantum field theory effects become important for that particle, where particle creation and annihilation cannot be ignored. A lighter particle has a larger Compton wavelength. An electron has a Compton wavelength of about 2.4 times 10 to the negative 12 meters. A proton, which is about 2,000 times heavier, has a Compton wavelength about 2,000 times smaller. Now consider the Schwarzschild radius. Every object with mass has a Schwarzschild radius, which is directly proportional to its mass. The Schwarzschild radius tells you the scale at which that mass would become a black hole. A larger mass has a larger Schwarzschild radius. For everyday objects, the Schwarzschild radius is absurdly tiny. The Schwarzschild radius of the Earth is about 9 millimeters, but for very massive or very compressed objects, it becomes relevant. Here is the key insight. The Compton wavelength decreases with increasing mass. The Schwarzschild radius increases with increasing mass. As you make a particle heavier and heavier, its quantum wavelength shrinks while its gravitational radius grows. At some mass, these two length scales become equal. That mass is the Planck mass, and the length at which they meet is the Planck length. For any particle lighter than the Planck mass, its Compton wavelength is larger than its Schwarzschild radius. This means quantum effects are more important than gravitational effects at that particle's characteristic scale. Such particles can be described by quantum mechanics without worrying about gravity. This includes all known elementary particles. For any object heavier than the Planck mass, its Schwarzschild radius is larger than its Compton wavelength. Gravity dominates over quantum effects at the relevant scale. Such objects can be described by general relativity without worrying about quantum mechanics. This includes all macroscopic objects. But at the Planck mass itself, at the Planck length itself, neither theory can be ignored. Both quantum effects and gravitational effects are equally important. And that is precisely where we need a theory of quantum gravity. The Planck length is the boundary between the quantum world and the gravitational world, and understanding what happens at that boundary is perhaps the greatest challenge in all of theoretical physics. Let me now explore what various approaches to quantum gravity actually say about the Planck scale. 2 in loop quantum gravity. As I mentioned earlier, space is quantized. But let me be more specific about what this means. In LQG, the fundamental excitations of the gravitational field are represented by spin networks. A spin network is a graph, a collection of nodes connected by links, where each link carries a quantum number, a half-integer value called a spin. These spins determine the geometry of space. Specifically, the area of any surface in space is determined by the spins of the links that puncture that surface, and the volume of any region is determined by the nodes of the spin network contained within that region. The spectrum of area in LQG is discrete. The smallest non-zero area is proportional to the Planck area and is approximately equal to 4 times the square root of 3 times pi times the Planck length squared, which works out to about 6.9 times 10 to the negative 70 meters squared. Similarly, volume has a discrete spectrum with the smallest non-zero value proportional to the Planck volume. This means that in LQG, you truly cannot have a surface with an area smaller than this minimum, or a region with a volume smaller than the minimum Planck volume. Space is genuinely quantized, with the Planck length setting the scale of the quanta. One of the most remarkable results of LQG is what it says about the Big Bang. When you apply the LQG equations to the early universe, the classical Big Bang singularity, the point where general relativity predicts infinite density and curvature, is resolved. Instead of a singularity, LQG predicts a big bounce. The universe was contracting, reached a minimum volume of approximately 1 Planck volume, and then began expanding. The singularity is replaced by a finite Planck scale event. This is a direct consequence of the quantum geometry predicted by LQG. The quantization of space prevents the universe from being compressed to zero size, just as the quantization of energy prevents an electron from falling into the nucleus of an atom. In string theory, the picture is quite different. The fundamental objects are not quanta of geometry, but one-dimensional strings. These strings vibrate in different patterns, and each pattern of vibration corresponds to a different particle. The electron, the photon, the graviton, all are different vibrational modes of the same fundamental string. The typical length of these strings is roughly the Planck length. The extended nature of strings automatically provides a minimum length scale. You cannot probe distances smaller than the string length, because the probe itself, being a string, cannot resolve distances smaller than its own size. String theory also introduces a fascinating mathematical relationship called T-duality that I mentioned briefly before but want to explore more deeply. T-duality says that a string theory compactified on a circle of radius r is physically equivalent to a string theory compactified on a circle of radius the square of the string length divided by r. So making the circle very small is the same as making it very large as far as the physics is concerned. The string length is the fixed point of this duality, the self-dual radius. This suggests that the concept of distance below the string scale is not simply undefined, but is equivalent to large distances. In a sense, there is no below the Planck scale in string theory, because below is the same as above. There is also an approach called causal dynamical triangulations, or CDIT, developed by Renat Lal, Jan Ambjorn, and Jerzy Jurkiewicz. In CDT, spacetime is built up from tiny building blocks, little triangular simplices, each with edge lengths at the Planck scale. The path integral of quantum gravity is computed by summing over all possible ways of assembling these building blocks into a spacetime. The remarkable thing about CDT is that it naturally produces a four-dimensional spacetime at large scales, even though it starts with no assumption about dimensionality. Even more remarkably, at very small scales, the effective dimensionality of spacetime appears to decrease from 4 to approximately 2. This phenomenon, called dimensional reduction, has been found in several independent approaches to quantum gravity, and may be a genuine property of Planck scale physics. The idea that spacetime might become effectively two-dimensional at the Planck scale is deeply connected to the holographic principle we discussed earlier. If the Planck scale spacetime is effectively two-dimensional, then a holographic description in terms of a two-dimensional theory is not just a mathematical trick, but a reflection of the underlying structure. The pixels of the hologram and the pixels of spacetime would be one and the same thing. Let us now turn to another profound connection between the Planck length and black holes. We have already discussed how trying to probe the Planck scale creates microscopic black holes. But there is much more to the relationship between Planck physics and black hole physics. A black hole is in many ways the ultimate Planck scale object projected to macroscopic size. The singularity at the centre of a black hole, if it exists in the classical sense, would be a region where spacetime curvature becomes Planck scale or beyond. The event horizon is the surface from within which nothing can escape, and the thermodynamic properties of black holes, their entropy, temperature and radiation, all involve Planck units in fundamental ways. Stephen Hawking's famous discovery in 1974 that black holes radiate thermal radiation brought quantum mechanics and gravity together in a concrete physical prediction. Hawking radiation arises from quantum fluctuations near the event horizon. The temperature of a black hole is inversely proportional to its mass. A solar mass black hole has a temperature of about 60 billionths of a degree above absolute zero, far too cold to detect. But a tiny black hole with the Planck mass would have a temperature equal to the Planck temperature, about 10 to the 32 degrees Kelvin. Such a black hole would evaporate almost instantaneously, in about 1 Planck time. The smallest possible black hole, if such a thing exists, would have a mass of approximately the Planck mass and a radius of approximately the Planck length. This is sometimes called a Planck particle or a maximon. It would be the most fundamental black hole possible, the smallest possible enclosure of information in the universe. Some physicists have speculated that such Planck-scale black holes might be the fundamental constituents of spacetime itself, that the quantum foam is made of them. This remains highly speculative, but it illustrates how deeply the Planck scale is connected to the physics of black holes. The information paradox of black holes is another place where the Planck scale plays a crucial role. When matter falls into a black hole, the information about its quantum state appears to be lost when the black hole evaporates through Hawking radiation, because the radiation is thermal and carries no information about what fell in. This contradicts a fundamental principle of quantum mechanics, which says that information is never lost. Resolving this paradox almost certainly requires understanding physics at the Planck scale, because the curvature at the centre of the black hole reaches Planck scale values, and the final stage of evaporation occurs when the black hole has shrunk to Planck size. Many proposed resolutions of the information paradox involve Planck scale physics. The fuzzball proposal in string theory replaces the classical black hole interior with a complex string theory object that has no singularity and no event horizon in the traditional sense, just a fuzzy quantum surface at the horizon scale. The firewall proposal suggests that the event horizon is not a gentle surface, but a wall of high-energy quanta. The soft hair proposal of Hawking, Perry and Strominger suggests that black holes carry additional quantum information in the form of soft particles living at the event horizon. All these proposals ultimately grapple with what happens at and near the Planck scale. Now I want to discuss something that might surprise you. The Planck length is not the only candidate for the minimum length in physics. Some physicists have argued that the actual minimum length might be somewhat larger than the Planck length, or that the concept of a minimum length might need to be formulated differently than a simple minimum distance. One important development in this area is the generalized uncertainty principle, or GUP. The standard Heisenberg uncertainty principle says that the uncertainty in position times the uncertainty in momentum is always greater than or equal to half of h bar. The GUP modifies this by adding a term proportional to the Planck length squared times the momentum squared. This additional term means that at very high energies, increasing the momentum of a probe does not keep shrinking the uncertainty in position. Instead, the uncertainty in position reaches a minimum value, which is of the order of the Planck length, and then starts increasing again. The GUP has been derived from string theory, from Gedanken experiments involving black holes, and from loop quantum gravity, and it provides a concrete mathematical formulation of the idea that there is a minimum measurable length. There are also physicists who argue that the minimum length might not be a hard cutoff, but rather a kind of fuzzy boundary. In some formulations, distances below the Planck length are not impossible, but become complex numbers, losing their physical interpretation. In others, the geometry of space at the Planck scale becomes non-commutative, meaning that the coordinates of space no longer commute with each other. In non-commutative geometry, the concept of a point in space breaks down, replaced by a minimum area cell. This provides yet another way of implementing a minimum length scale. Let me now address some common misconceptions about the Planck length, because there are several ways in which it is often misunderstood or misrepresented. The first misconception is that the Planck length is the smallest possible length. This is often stated in popular science, but is not quite correct. The Planck length is the scale at which our current theories break down, and a theory of quantum gravity becomes necessary. It may or may not be the actual smallest length. Some theories do predict a hard minimum length at the Planck scale, others do not. It is more accurate to say that the Planck length is the smallest scale at which the concept of length, as we currently understand it. Make sense? What happens below that scale is unknown and might involve entirely new concepts that do not correspond to our intuitive notion of distance. The second misconception is that space is made of tiny cubes or tiny dots arranged in a regular grid, like pixels on a computer screen. This is a common visualization, but is almost certainly wrong. If space were a regular grid, it would pick out preferred directions and break the symmetry of space. We know from experimental evidence that space is isotropic, the same in all directions, to extremely high precision. Any discreteness of space must be compatible with this isotropy, which means it cannot be a simple regular lattice. The discrete structures proposed by actual quantum gravity theories, like spin networks in LQG or causal sets, are much more complex and do not resemble a simple grid. The third misconception is that particles or objects smaller than the Planck length cannot exist. In fact, several objects in theoretical physics have sizes that are, in some sense, smaller than the Planck length. The point is that their size cannot be resolved or measured below that scale. A string in string theory, for example, can be compressed to be smaller than the Planck length, but when you do so, T-duality maps it back to something larger than the Planck length. The physical observables never actually go below the Planck scale, even if the mathematical description might suggest they do. The fourth misconception is that the Planck length is related to the pixel size of a simulation. The idea that we might be living in a computer simulation is a popular philosophical thought experiment, and people sometimes point to the Planck length as evidence, arguing that a digital simulation would have a minimum resolution just like the Planck length. While this is an intriguing analogy, it is important to note that the existence of a minimum length scale does not require or imply a simulation. Minimum lengths arise naturally from the physics of quantum mechanics and gravity without any need for a computer. The Planck length is a consequence of the fundamental constants of nature, not evidence for a programmer. Now let us talk about the Planck temperature, because it connects the Planck length to some truly extreme physics. The Planck temperature is approximately 1.4 2 × 10 to the 32 degrees Kelvin. This is unimaginably hot. The centre of the Sun is about 15 million degrees. A supernova explosion reaches about 10 billion degrees. The hottest thing we have ever created on Earth in particle accelerator collisions is about 5.5 trillion degrees. The temperature at the core of a neutron star merger is about 100 billion degrees. Even the temperature of the universe at 1 microsecond after the Big Bang was only about 10 trillion degrees. The Planck temperature is approximately 10 to the 20 orders of magnitude higher than any of these. At the Planck temperature, the thermal energy of particles equals the Planck energy. Particles at this temperature would have wavelengths comparable to the Planck length, meaning they would directly probe the quantum gravitational structure of spacetime. The Planck temperature is the maximum physically meaningful temperature if the Planck length is the minimum meaningful length, because heating something beyond this point would just produce particles that collapse into Planck-sized black holes. It is, in a sense, the maximum temperature the universe allows. The early universe reached the Planck temperature during the Planck epoch. As the universe expanded and cooled from this temperature, the different forces of nature separated out one by one, the fundamental particles acquired their masses, and the universe evolved into what we see today. Every structure in the universe, every galaxy, star, planet, and living creature is the result of a long cooling from the Planck temperature. We are made of cooled Planck temperature fire, in a metaphorical sense. Let me now explore a thought experiment that makes the peculiarity of the Planck length viscerally clear. Imagine you are a scientist with unlimited resources. You want to build the ultimate microscope, one that can resolve the Planck length. What would you need? First, you would need a particle accelerator. The energy required to probe the Planck length is about 10 to the 19 billion electron volts. The most powerful accelerator currently in existence, the Large Hadron Collider, reaches energies of about 13 trillion electron volts, or about 10 to the 4 billion electron volts. So you need an accelerator roughly 1 quadrillion times more powerful than the LHC. If you were to build a circular accelerator using the same magnetic field strength as the LHC, it would need to be approximately 10 to the 12 kilometers in circumference. That is about 1 light year. You would need an accelerator the size of the orbit of the nearest star system. Even with far more advanced technology, a Planck energy accelerator would require fantastical engineering far beyond anything we can currently conceive. But here is the deeper problem. even if you could build such an accelerator, it would not work as a microscope. When you collide two particles at Planck energy, the concentration of energy in such a small region would create a black hole. Your microscope would create a black hole every time you tried to use it, and the black hole would swallow whatever you were trying to observe. This is not an engineering problem you can overcome with better technology. It is a fundamental property of nature. The universe does not allow you to see below the Planck length, not because you are not clever enough, but because the laws of physics conspire to prevent it. Some physicists find this deeply suggestive. They argue that the universe's refusal to be probed below the Planck scale is a hint that there is nothing below the Planck scale, that the Planck length is not just a practical limit, but an absolute boundary. That space does not exist below this scale, because there is nowhere for it to exist. Others are more cautious and argue that our inability to probe below the Planck scale is simply a limitation of our current theoretical framework, and that a future theory of quantum gravity might reveal a rich structure below the Planck length that we simply cannot access yet. There is actually a beautiful analogy for this situation. Before the development of statistical mechanics in the 19th century, the concept of temperature seemed like a continuous quantity that could increase without limit and decrease to any value. Then physicists realized that temperature is actually related to the kinetic energy of molecules, and that there is a natural lower limit, absolute zero, at which molecular motion stops. You cannot go below absolute zero, not because of any limitation of thermometers, but because temperature is a measure of molecular motion and you cannot have less than no motion. Similarly, the Planck length might be the absolute zero of distance. You cannot go below it, not because of any limitation of rulers, but because distance is a property of space-time geometry, and you cannot have less than one quantum of geometry. Let us now delve into one more fascinating topic that connects the Planck length to the nature of reality itself. This is the question of whether the universe is, at its most fundamental level, made of information. In 1990, John Archibald Wheeler, the same physicist who proposed quantum foam, coined the phrase "it from bit." He proposed that every physical quantity, every particle, every force, every space-time event derives its existence entirely from information. The universe at bottom is not made of matter or energy or space-time, but of bits of information. And those bits are encoded at the Planck scale. This idea has gained significant traction in recent decades, particularly through developments in black hole physics, the holographic principle, and quantum information theory. The Bekenstein bound, which relates the maximum information content of a region to its surface area in Planck units, strongly supports the idea that information is fundamental, and that the Planck area is the fundamental unit of information storage. If we take this idea seriously, then the Planck length squared is not just the minimum area, it is the size of one bit. Each Planck area on any surface can store exactly one bit of information, a 0 or a 1. The universe is then like a vast cosmic hard drive, written in binary at Planck scale resolution. Every physical process, every interaction between particles, every gravitational wave, every thought in your brain, is ultimately a computation performed on this Planck scale binary substrate. This perspective does not necessarily mean the universe is a simulation in the sense of being computed by some external computer. It means that information is the fundamental substance of reality, and computation is the fundamental process. The laws of physics are the rules of the computation, and the Planck scale is the scale at which individual bits are stored and processed. This is a radical ontological claim, and not all physicists accept it, but it is supported by a growing body of theoretical evidence, and it places the Planck length at the very centre of our understanding of what reality fundamentally is. Let me now step back and consider the Planck length from a broader philosophical perspective. Throughout the history of physics, we have repeatedly discovered that quantities we thought were continuous are actually discrete. Energy is discrete. Electric charge is discrete. Angular momentum is discrete. matter is discrete. Even the forces between particles are discrete. In every case, the discovery of discreteness was accompanied by a fundamental constant that set the scale of the discreteness. If space is also discrete, and the Planck length sets the scale of that discreteness, then we would be discovering perhaps the most fundamental discreteness of all. Space is the stage on which everything else happens. If the stage itself is pixelated, then everything that happens on it is ultimately digital. The universe would be, at its deepest level, a discrete structure. Not continuous, not smooth, not infinitely divisible, but fundamentally grainy at the Planck scale. This would also resolve some ancient philosophical puzzles. Zeno of Elea, a Greek philosopher who lived around 500 years before the Common Era, posed several paradoxes about motion. One of the most famous is the paradox of the arrow. An arrow in flight, Zeno argued, must at any single instant be at a particular position. At each instant, it is not moving. But if it is not moving at any single instant, how does it ever move? The paradox assumes that time and space are infinitely divisible, so that there are infinitely many instants between any two moments. If space and time are discrete, if there is a minimum distance and a minimum time, then Zeno's paradox dissolves. The arrow does not pass through infinitely many positions. It passes through a finite number of Planck length steps, and the paradox evaporates. Of course, resolving ancient philosophical paradoxes is not the primary motivation for studying the Planck length. The primary motivation is understanding the fundamental nature of reality. And the Planck length sits at the very frontier of that understanding. Let me now discuss something that might seem surprising. Despite its theoretical importance, the Planck length has never been directly measured or observed. We infer its significance purely from the mathematical structure of our theories and from thought experiments about what would happen if we tried to probe very small distances. No experiment has ever directly probed the Planck scale. No measurement has ever directly confirmed that space is discrete or that the Planck length is a true minimum length. Everything we know about the Planck scale is theoretical. This is both humbling and exciting. It is humbling because it means our understanding of the Planck scale could be incomplete or even wrong. Maybe space is not discrete. Maybe there is no minimum length. Maybe our theoretical arguments have led us astray. It is exciting because it means there is a vast unknown waiting to be discovered. The Planck scale is the ultimate frontier of physics, and whoever manages to experimentally probe it will make one of the greatest discoveries in the history of science. There are some indirect experimental constraints that give us confidence that the Planck length is physically meaningful. The success of quantum mechanics and general relativity separately, both tested to extraordinary precision, combined with the dimensional analysis argument that they must break down when combined at the Planck scale, gives us strong theoretical reasons to believe the Planck length is physically significant. The Fermi telescope observations I mentioned earlier have confirmed that the speed of light is constant to 1 part in more than 10 to the 19, even for photons that have travelled billions of light years, which is consistent with a Planck scale minimum length. Various quantum gravity phenomenology proposals continue to search for indirect signatures of Planck scale physics in cosmological observations, gravitational wave signals, and high-energy astrophysics. Now let us discuss the Planck length in the context of the vacuum of space. Many people think of the vacuum as empty, as nothing, but modern physics tells us the vacuum is anything but empty. It is seething with activity. Virtual particles are constantly being created and destroyed. Quantum fields fluctuate around their ground states. The vacuum has energy, called zero-point energy or vacuum energy. And at the Planck scale, these vacuum fluctuations become so intense that they might distort the geometry of spacetime itself. The energy density of the vacuum is one of the most embarrassing problems in all of theoretical physics. If you naively calculate the vacuum energy by summing up the zero-point energies of all quantum fields up to the Planck scale, you get a value of approximately 10 to the 113 joules per cubic meter. This is a fantastically enormous energy density. However, the observed vacuum energy density, measured from the accelerating expansion of the universe, is only about 10 to the negative 9 joules per cubic meter. The discrepancy between the theoretical prediction and the observed value is a factor of about 10 to the 122. This is sometimes called the worst prediction in all of physics. This cosmological constant problem is intimately connected to the Planck scale. The huge predicted value comes from integrating quantum fluctuations up to the Planck energy. Something must cancel or suppress these contributions by a factor of 10 to the 122, but we do not know what. This problem has been called the most important unsolved problem in theoretical physics, and solving it almost certainly requires understanding quantum gravity and Planck scale physics. Let me now talk about another fascinating theoretical development related to the Planck length. This is the concept of minimum length in the context of doubly special relativity, or deformed special relativity, developed by Giovanni Amelino Camiglia starting around 2000. In standard special relativity, there is one observer-independent scale, the speed of light c. All observers, regardless of their motion, agree on the value of c. Amelino Camiglia proposed that there might be a second observer-independent scale, a minimum length, which he identified with the Planck length. Just as all observers agree that nothing can go faster than light, all observers would agree that no distance can be smaller than the Planck length. This might sound obvious, but it is actually quite tricky to implement mathematically. In standard special relativity, lengths contract when you move at high speeds. So if you have a rod that is 1 Planck length long and you fly past it at high speed, would it not appear shorter than 1 Planck length? In doubly special relativity, the laws of physics are modified at very high energies in such a way that the Planck length is invariant, not subject to Lorentz contraction, just as the speed of light is invariant, not subject to velocity addition. This requires a deformation of the standard symmetries of special relativity, which is why it is called deformed special relativity. Whether doubly special relativity is correct is still debated. It makes specific predictions about how high-energy particles should behave, and some of these predictions are potentially testable with observations of ultra-high-energy cosmic rays or gamma-ray bursts. But the predictions are extremely subtle, and current experiments have not definitively confirmed or ruled out the theory. Let me now weave together several threads we have been discussing and paint a picture of what the Planck scale might really be like, based on the best theoretical understanding we have. At the Planck scale, space as we know it ceases to exist. The smooth, continuous three-dimensional space that we experience in everyday life is revealed to be an approximation, an illusion that only holds at scales much larger than the Planck length. Zoom into the Planck scale, and this smooth space dissolves into something else entirely. What that something else is depends on which theory of quantum gravity you believe, but common features emerge across different approaches. First, geometry becomes quantum. Just as the energy of an electron in an atom can only take certain discrete values, the geometry of space at the Planck scale can only take certain discrete values. Area and volume come in specific quantum units. The smooth curves of spacetime give way to a discrete combinatorial structure, a network of quantum relationships. Second, spacetime becomes uncertain. Just as a particle in quantum mechanics does not have a definite position until you measure it, a region of space at the Planck scale does not have a definite geometry until it is measured. The geometry of space fluctuates, exists in superposition of different configurations, and only settles into a definite state when interacted with. Third, the distinction between space and time may break down. In our everyday experience, space and time are clearly different. Space is extended in 3 dimensions, time flows in one direction. But at the Planck scale, the causal structure that distinguishes space from time might become blurred. Multiple approaches to quantum gravity suggest that the usual clear separation of space-time into space and time is an emergent property of the large-scale description, not a fundamental property of the Planck scale physics. Fourth, the very concept of dimensionality might be scale-dependent. As I mentioned earlier, several approaches to quantum gravity find that the effective dimensionality of space-time decreases at very small scales, approaching 2 dimensions at the Planck scale. Our familiar 4-dimensional space-time might be a large-scale phenomenon, with the fundamental Planck scale physics being essentially 2-dimensional. Fifth, information might be primary. Rather than space being a container for information, information might be the thing that gives rise to space. The emergence of spacetime from quantum entanglement, an idea that has been explored extensively in recent years through the ER=EPIR conjecture and related developments, suggests that the connectivity of space is created by quantum correlations between fundamental degrees of freedom. At the Planck scale, these degrees of freedom are individual bits, and their entanglement pattern determines the geometry of the emergent spacetime. This brings us to one of the most exciting developments in theoretical physics in recent decades: the idea that spacetime emerges from entanglement. In 2006, Shinsei Ryu and Tadashi Takeyanagi discovered a remarkable formula relating the entanglement entropy of a region in a quantum field theory to the area of a surface in the Joule gravitational theory. Their formula showed that the amount of quantum entanglement between 2 regions of a quantum system is directly proportional to the area of the surface connecting them in the corresponding gravitational description, measured in Planck units. This was later extended by Mark van Ramsdonk, who argued in an influential paper in 2010 that quantum entanglement is what holds spacetime together. If you remove the entanglement between 2 regions of a quantum system, the corresponding regions of spacetime become disconnected. Spacetime literally tears apart when entanglement is destroyed. Conversely, creating entanglement between previously unentangled degrees of freedom creates new connections in spacetime. In this picture, the geometry of space is not fundamental, but emerges from the pattern of quantum entanglement among the Planck scale degrees of freedom. This has led to the slogan that entanglement is the glue of spacetime. The Planck scale bits are connected to each other by quantum entanglement, and the pattern of these connections determines the geometry of space at larger scales. A flat region of space corresponds to a particular pattern of entanglement. A curved region of space, such as near a massive object, corresponds to a different pattern. A black hole corresponds to a particularly extreme pattern of entanglement. And a disconnected spacetime, a region of space that is topologically separate from the rest, would correspond to a complete absence of entanglement. If this picture is correct, then the Planck length is not just the minimum resolution of space. It is the size of the fundamental building blocks from which space is constructed. Space is built from Planck-sized bits, connected by entanglement, and the particular pattern of connections determines the geometry we observe at large scales. The pixel analogy in this context becomes remarkably apt. Each Planck area is like a pixel that can be in one of 2 states, and the arrangement of these pixels creates the image we call spacetime. Let me now turn to a related but distinct topic: the relationship between the Planck length and the arrow of time. We all experience time as flowing in one direction, from past to future. Glasses shatter but do not reassemble. People age but do not grow young. This directionality of time, called the arrow of time, is one of the deepest puzzles in physics, because the fundamental laws of physics are symmetric in time. They do not prefer any direction. So where does the arrow of time come from? One possible answer involves the Planck scale. If spacetime geometry is determined by quantum entanglement at the Planck scale, and if the second law of thermodynamics applies to this entanglement, then the arrow of time might emerge from the growth of entanglement at the Planck scale. As Planck scale degrees of freedom become increasingly entangled over time, the geometry of space-time changes in a way that corresponds to our experience of time flowing forward. The arrow of time would not be put in by hand, but would emerge naturally from the quantum dynamics of the Planck scale substrate. This is speculative, but represents an active area of research connecting quantum information theory, quantum gravity, and thermodynamics. The Planck length sits at the intersection of all these fields, serving as the fundamental scale at which the deepest questions about the nature of reality converge. Let me now discuss a topic that is often raised in connection with the Planck length, but is frequently misunderstood. That is the simulation hypothesis and its relationship to the idea of a minimum length. Some people argue that the existence of the Planck length as a minimum resolution of space is evidence that we live in a computer simulation, reasoning that a simulation would necessarily have a finite resolution, and the Planck length is that resolution. While this is an intriguing philosophical thought experiment, it is important to understand why this argument does not actually work as evidence. First, as we have discussed, the Planck length as a minimum resolution arises naturally from the combination of quantum mechanics and general relativity. No external simulator is needed to produce it. It emerges from the internal logic of the physics itself. Second, even if we do live in a simulation, the Planck length might not be the resolution of the simulation. The simulation might have much finer resolution. The Planck length might just be a physical scale within the simulated physics, not a limitation of the underlying hardware. Third, the simulation hypothesis is not scientific in the strict sense because it makes no unique testable predictions. Any observation can be explained as a feature of the simulation. This makes it unfalsifiable and therefore outside the domain of empirical science. None of this means the simulation hypothesis is wrong. It might be correct, but the Planck length should not be taken as evidence for it. The Planck length is interesting and important on its own merits as a feature of our physical universe, regardless of whether that universe is simulated or fundamental. Let me now discuss something quite different but equally fascinating: the relationship between the Planck length and the anthropic principle. The anthropic principle, in its weak form, says that we should not be surprised to find ourselves in a universe that is compatible with our existence. After all, we could not exist in a universe that was not compatible with our existence. Now consider the following. The Planck length depends on three constants, h bar, g, and c. These constants have specific numerical values in our universe. If they had different values, the Planck length would be different, and the physics of the universe would be profoundly altered. For example, if the gravitational constant g were much larger, the Planck length would be larger, and quantum gravitational effects would become important at larger scales. This would make it difficult or impossible for complex structures like atoms, molecules, and living organisms to exist. Because the stable structures of matter rely on the weakness of gravity at small scales. Similarly, if Planck's constant were much larger, quantum effects would manifest at larger scales, making the world much fuzzier and more probabilistic than it is. The stable structures we rely on, atoms with definite electron shells, molecules with definite shapes, might not form. If the speed of light were different, the entire structure of electromagnetism and special relativity would change, altering the nature of atoms and chemistry. The fact that the Planck length is so incredibly small, at 10 to the negative 35 meters, means that quantum gravitational effects are completely irrelevant at the scales of atoms, molecules, and everyday life. This separation of scales, 16 orders of magnitude between the Planck length and the atomic scale, is what allows complex chemistry and biology to exist without being disrupted by quantum gravity fluctuations. In a sense, we exist because the Planck length is so small. If it were closer to the atomic scale, the universe would be a quantum gravitational chaos in which no stable structures could form. Whether the values of the fundamental constants require explanation, or whether they are simply brute facts, is a deep and unresolved question. But it is worth noting that our existence depends on the Planck length being many orders of magnitude smaller than the scales relevant to life. Now let me bring us back to the experimental frontier. What are physicists actually doing right now to try to learn about the Planck scale? I have mentioned several approaches already: the Fermi telescope observations, the holometer at Fermilab, gravitational wave detectors. But there are other avenues being pursued. One exciting approach involves using quantum optics and precision measurement techniques to search for signatures of Planck scale physics in laboratory experiments. The idea is that even though we cannot directly probe the Planck scale, the discreteness of space-time at that scale might leave subtle imprints on physics at accessible scales, just as the quantum mechanics of atoms leaves imprints on the macroscopic properties of materials. For instance, if there is a minimum length, it would modify the uncertainty principle. This modification might be detectable in extremely precise measurements of the position and momentum of particles, or in the behavior of quantum harmonic oscillators, or in the energy levels of atoms. Several groups around the world are working on experiments designed to test these predictions, though the effects are predicted to be extraordinarily small, and current experiments have not yet reached the sensitivity needed to detect them. Another approach uses cosmological observations. The cosmic microwave background, the afterglow of the Big Bang, carries information about the very early universe when energy densities were much closer to the Planck scale. Detailed analysis of the statistical properties of the cosmic microwave background might reveal signatures of Planck scale physics from the early universe, imprinted on the pattern of temperature fluctuations we observe today. The Planck satellite has measured the cosmic microwave background with extraordinary precision, and its data is consistent with standard cosmological predictions. But future experiments with even greater sensitivity might detect subtle deviations that point to Planck scale physics. There is also the possibility that quantum gravity effects might be detectable in the behavior of gravitational waves. When two black holes merge, the geometry of spacetime near the merger reaches extreme curvatures. While these curvatures are still far below the Planck scale for the mergers we have observed so far, the detailed waveform of the gravitational signal might carry subtle corrections from Planck scale physics. Future gravitational wave detectors, such as the space-based LISA mission or next-generation ground-based detectors, might be sensitive enough to detect such corrections. Perhaps the most promising approach involves studying the behavior of systems that amplify quantum effects to macroscopic scales. For instance, some proposals suggest that the decoherence rate of quantum superpositions of massive objects might be affected by quantum gravity effects at the Planck scale. If spacetime is discrete, or fuzzy at the Planck scale, it might cause massive objects in quantum superposition to decohere faster than standard quantum mechanics predicts. Experiments testing quantum superposition of increasingly massive objects, such as the proposals to put small mirrors or microbeads in superposition, might eventually be sensitive to these effects. Let me now take a step back and reflect on what the Planck length tells us about the scientific enterprise itself. The story of the Planck length is, in many ways, the story of how far human curiosity and ingenuity can reach. We are creatures about 1.7 meters tall, living on a small planet orbiting an ordinary star in one of hundreds of billions of galaxies. We perceive the world at scales from about 1/10 of a millimeter to about a few kilometers. Yet through the power of mathematics, experiment, and logical reasoning, we have deduced the existence of a length scale 35 orders of magnitude smaller than anything we can directly perceive. We have never seen the Planck length. We have never measured it directly. We may never be able to. Yet we are reasonably confident it exists as a meaningful physical scale, based on the internal consistency of our theories and the thought experiments that reveal what happens when quantum mechanics and gravity collide. This is the power of theoretical physics at its best. It can reach beyond the limits of direct experience and reveal truths about nature that are completely invisible to our senses. At the same time, the Planck length reminds us of our limitations. It represents a wall that may be permanently beyond our experimental reach. It reminds us that there may be aspects of reality that we can theorize about, but never directly verify. This is a sobering thought for a species that has built its scientific progress on the foundation of experimental verification. If the Planck scale remains permanently beyond experiment, we may have to develop new standards for what constitutes knowledge and what counts as a valid theory. This is an active philosophical debate in the foundations of physics today. Let me now bring together all the threads we have explored and paint a final, comprehensive picture of what the Planck length means for our understanding of reality. The Planck length is the scale at which the three pillars of modern physics, quantum mechanics, special relativity, and general relativity, all become simultaneously important and mutually incompatible. It is the scale at which our theories break down and demand something new. It is the scale at which space, time, matter, and energy may all be fundamentally different from what we experience at everyday scales. At the Planck length, space may be discrete rather than continuous, pixelated rather than smooth. Geometry may be quantum rather than classical, uncertain rather than definite. The familiar concepts of distance, area, and volume may acquire minimum values, below which they lose meaning. The distinction between space and time may blur. Information may be more fundamental than geometry. Entanglement may be more fundamental than space. The Planck length was at the centre of the Big Bang, where the universe was born from a Planck-sized quantum event. It is at the centre of black holes, where space-time curvature reaches Planck scale values. It determines the entropy and temperature of black holes through the Bekenstein-Hawking formulas. It sets the resolution of the holographic principle, determining how much information can be stored on a given surface. It defines the scale of quantum foam, if quantum foam exists. It appears in the generalized uncertainty principle as the minimum measurable distance. It is the self-dual point of T-duality in string theory. It is the scale of the quanta of area and volume in loop quantum gravity. It is the spacing between elements in causal set theory. The Planck length connects the deepest questions in physics. What is space? What is time? What is information? How did the universe begin? What happens inside black holes? How do quantum mechanics and gravity unite? What is the fundamental nature of reality? All these questions converge at the Planck scale. Whoever answers these questions will understand what happens at the Planck length. And whoever understands what happens at the Planck length will have answered these questions. And now I want to share with you a research result that I find particularly beautiful and that brings many of our themes together. In 2012, a paper by Eric Valinde proposed an idea called entropic gravity, building on earlier work on the holographic principle and black hole thermodynamics. Valinde suggested that gravity itself is not a fundamental force, but an entropic force, arising from the statistical tendency of information to arrange itself in certain ways at the Planck scale. Just as the pressure of a gas arises not from any force law between individual molecules, but from the statistical mechanics of many molecules, gravity might arise from the information dynamics of many Planck scale bits. In this picture, Newton's law of gravity and even Einstein's general relativity are emergent, approximate descriptions of what is fundamentally an information-theoretic process occurring at the Planck scale. If Valinde's entropic gravity is correct, then the implications are profound. It would mean that the deepest level of reality is informational, not geometric. Space and gravity would be emergent phenomena arising from the behaviour of Planck scale information. The pixel analogy we started with would be not just a metaphor, but a literal description of reality. The universe really would be made of Planck-sized bits, and everything we experience, every object, every force, every thought, would be patterns in these bits. This connects to another stunning theoretical development. In 2015, Leonard Susskind proposed the concept of quantum complexity as a geometric property of spacetime. He suggested that the complexity of the quantum state of a system, meaning how many simple operations are needed to construct that state from a simple starting point, is related to the geometry of the interior of black holes and of spacetime in general. The growth of complexity over time corresponds to the growth of spacetime geometry, specifically to the growth of the Einstein-Rosen bridge inside a black hole. And the fundamental unit of complexity is the Planck scale operation. The universe, in a sense, computes its own geometry one Planck scale operation at a time, with each operation adding one Planck unit to the length of the wormhole. These are cutting-edge ideas at the very frontier of theoretical physics. They may prove correct, or they may be superseded by better ideas. But they all point in the same direction. The Planck length is not merely a curiosity or a mathematical artifact. It is telling us something profound about the fundamental structure of reality. It is the scale at which the universe reveals its deepest nature. An understanding that nature is the great project of 21st century physics. Let me now turn to a more concrete and historically grounded discussion. I want to tell you about the various attempts that have been made over the past century to understand quantum gravity and the Planck scale, and what progress we have made. The quest for quantum gravity began almost immediately after the development of general relativity and quantum mechanics. In 1930, Leon Rosenfeld made the first attempts to quantize gravity using the same techniques that had successfully quantized electromagnetism. These attempts quickly ran into trouble. The resulting theory was plagued by infinities that could not be removed by the standard renormalization techniques that work for electromagnetism. Unlike quantum electrodynamics, quantum gravity appeared to be non-renormalizable, meaning that it produced an infinite number of infinities that could not be consistently handled. This problem persisted for decades. Many of the greatest physicists of the 20th century, including Richard Feynman, Bryce DeWitt and others, worked on it without resolution. In 1967, DeWitt derived what is now called the Wheeler-DeWitt equation, a quantum equation for the entire universe that plays the role of the Schrödinger equation for quantum gravity. But this equation proved extraordinarily difficult to solve or even interpret. It implies that the wave function of the universe does not evolve in time, leading to the so-called problem of time in quantum gravity. If the fundamental equation has no time in it, where does our experience of time come from? In the 1980s, two major new approaches emerged that transformed the landscape. In 1984, Michael Green and John Schwartz showed that string theory could consistently incorporate gravity, leading to the first superstring revolution. String theory resolved the infinities of quantum gravity by replacing point particles with extended strings, smoothing out the Planck scale singularities that plagued the point particle approach. Over the following decades, string theory developed into a rich mathematical framework with many remarkable properties but also many challenges, including the lack of unique predictions and the enormous landscape of possible solutions. In 1986, Abhay Ashtekar reformulated general relativity in a way that made it more amenable to quantization, leading to the development of loop quantum gravity. Q takes a different approach from string theory. Instead of adding new ingredients, it quantizes general relativity directly, finding that the geometry of space itself becomes quantum and discrete at the Planck scale. Q has produced concrete predictions about the quantum structure of space, including the spectrum of area and volume operators, but it has its own challenges, including reproducing the full dynamics of gravity and making contact with low-energy physics. In the 1990s, several other approaches emerged. Causal set theory, initiated by Raphael Sorkin, proposed that spacetime is fundamentally a partially ordered set of discrete elements. Causal dynamical triangulations, developed by Loll, Hamborn and Jerkiewicz, used computational techniques to study quantum gravity non-perturbatively. The asymptotic safety program, pioneered by Martin Reuter, investigated whether gravity might be non-perturbatively renormalizable after all, with the coupling constants flowing to a fixed point at the Planck scale. Then came 2017 and a revolutionary development, the discovery by Maldacena in 1997 of the ADS-CFD correspondence, which showed that a theory of quantum gravity in a certain type of spacetime is exactly equivalent to a quantum field theory without gravity living on the boundary of that spacetime. This was the most concrete realization of the holographic principle, and provided the first exact definition of quantum gravity in certain spacetimes. It showed that quantum gravity, at least in these special spacetimes, is well defined and non-perturbatively consistent. The Planck scale in the gravitational description corresponds to the ultraviolet physics in the boundary theory. As of my knowledge, no single approach to quantum gravity has achieved the status of a confirmed theory. We do not know which, if any, of the current approaches is correct. The experimental evidence needed to distinguish between them remains beyond our reach. But the theoretical progress over the past century has been enormous, and we now have multiple mathematically consistent frameworks for thinking about Planck scale physics, each with its own insights and predictions. Let me now discuss one more profound aspect of the Planck length that we have not yet touched on. This is its relationship to the nature of infinity. In classical physics, space is continuous and infinitely divisible. Between any 2 points, no matter how close, there are infinitely many intermediate points. The real number line, which mathematicians use to model space, contains uncountably infinite many numbers in any interval, no matter how small. This infinite divisibility is usually taken for granted, but it leads to some disturbing consequences.